Section 1.1.7 Elasticity and Scaling Horizontal versus Vertical. Scaling in the cloud is one of those topics that sounds simple, but is often misunderstood. Many people think it's about making systems bigger. But that's not really the point. Scaling is about something more precise. It's about matching changing demand with controlled capacity, without breaking the system, and without wasting resources. That is the real problem cloud platforms are built to solve. And when you slow down and look at it carefully, there are only two fundamental ways to do this. You either scale vertically or you scale horizontally. Let's start with the simpler one. Imagine a system where nothing about the design changes, but one part of it becomes stronger. That's vertical scaling. Vertical scaling means increasing the power of a single compute node. You don't redesign the system. You don't introduce new components. You simply give more resources to what already exists. In practical terms, this usually means more CPU cores, more memory, and faster storage. The architecture stays exactly the same, only the capacity of a single unit increases. This approach is extremely common in real production systems, especially in the early stages. In fact, when people casually say, "We need to scale," this is often what they have in mind. On Amazon Web Services, for example, vertical scaling means resizing an EC2 instance from a smaller type to a larger one. In practice, this often requires stopping the instance and starting it again, or replacing it with a new one. In Azure SQL database, vertical scaling means moving to a higher service tier. In Google Cloud SQL, it means migrating the same database to a larger instance class. Vertical scaling is attractive because it's simple. There's very little architectural overhead, and teams can move fast. That's why many systems begin this way. But vertical scaling has a hard limit. There is always a ceiling. CPU can only grow so much. Memory can only grow so much. Even network throughput eventually reaches physical limits. And there's another drawback that matters even more. Vertical scaling does not improve fault tolerance. If that single node fails, because of hardware issues, software bugs, or a bad deployment, the entire workload fails with it. You gain more capacity, but you don't gain more resilience. This point is subtle but important. It's also something experienced engineers tend to emphasize when explaining scaling decisions. A clear way to express it is this: vertical scaling improves capacity, but it does not improve availability, because the system still depends on a single node. Cost is part of the story as well. Vertical scaling can be expensive up front. Larger instances cost more per hour, and pricing rarely scales linearly. At the same time, this approach avoids much of the operational complexity of distributed systems. No load balancers, no coordination between nodes, no data synchronization logic. For small teams and predictable workloads, that trade-off often makes sense. Now let's look at the other approach. There's another way to scale, and it requires a different way of thinking. Instead of making one unit stronger, you add more units and let them work together. Capacity grows because the workload is shared. That's horizontal scaling. This is what people usually mean when they talk about systems that scale elastically. Horizontal scaling works best when compute nodes are stateless. In other words, when individual nodes don't hold critical state themselves. Any important state should live in external, persistent storage. If that's not the case, horizontal scaling quickly becomes difficult. Let's ground this in real examples. Kubernetes is a good one. It's a container orchestration system that runs applications in units called pods. When traffic goes up, Kubernetes can automatically add more pods. When traffic goes down, it removes them. That's horizontal scaling at the container level. AWS Lambda follows the same principle. Just without servers, you manage yourself. As request volume increases, the platform automatically increases concurrency. You focus on the code, the infrastructure adapts on its own. Another common example is EC2 auto-scaling. Here, virtual machines are created or terminated based on metrics like CPU usage or request rate. That's horizontal scaling at the virtual machine layer. You see the same idea in event-driven systems. Kafka consumer groups scale by adding more consumers to process messages in parallel. SQS-based worker systems do the same when message backlogs grow. a clear pattern emerges. Horizontal scaling relies on having multiple interchangeable compute units. If one unit fails, the others continue working. That's where availability and resilience come from. From a cost perspective, horizontal scaling can be very efficient when demand fluctuates. You scale down during quiet periods and scale up only when needed. But this only works with good observability. Without accurate metrics and sensible thresholds, systems either scale too much and waste money, or don't scale enough and fail under load. That's why monitoring and alerting are part of scaling itself, not something added later. This leads to another important insight. Scaling is not just about adding nodes, it's about knowing when to add them. At this point, the question isn't which approach is better, but which one fits the workload. Strengthening a single resource works well for certain types of systems, especially those that are state-heavy, memory-intensive, latency-sensitive, or tightly bound to local data. A PostgreSQL primary node is a classic example. The write path is transactional, and distributing writes introduces significant complexity. That's why many production databases scale vertically before doing anything else. Redis follows a similar pattern. As an in-memory data store, it benefits enormously from having more memory and CPU in a single primary node. Analytical workloads often behave the same way. Single-node Spark jobs or data processing pipelines frequently scale vertically first, especially when the data fits in memory. Vertical scaling also works well when traffic is predictable. Steady demand, without sudden spikes. It simplifies debugging too. Fewer moving parts usually mean fewer things that can go wrong. Other systems behave very differently. Workloads that are stateless, request-driven, traffic variable, and easy to parallelize are a natural fit for horizontal scaling. API services behind a load balancer are the textbook example. Each request is independent, so adding more nodes directly increases throughput. Event-driven worker systems behave the same way. As queues grow, workers scale up. As queues shrink, they scale down. Microservices running in Kubernetes fit naturally into this model. They scale pod counts based on CPU usage, latency, or custom metrics. Horizontal scaling increases capacity, but it also improves resilience. That's why it shines in unpredictable environments, like e-commerce during sales, or social platforms during viral spikes. Of course, this approach introduces new challenges: network latency, coordination between services, eventual consistency. A senior explanation doesn't ignore these issues. It acknowledges the trade-offs. If you step back and look at real cloud systems, one thing becomes clear. Scaling is almost never purely vertical or purely horizontal. Most architectures combine both. The compute layer usually scales horizontally. Pods, Lambda functions, and autoscaling groups come and go as demand changes. The data layer, on the other hand, often scales vertically first. Only later does it scale horizontally through techniques like read replicas or sharding. The key insight is simple. There is no universally correct scaling strategy. The right choice depends on the workload. CPU-bound systems often benefit from vertical scaling. Input-output bound or request parallel systems often benefit from horizontal scaling. That's why experienced engineers look at metrics before preferences. They measure, they test, they iterate. If there's one idea from this section worth keeping, it's this. Vertical scaling increases the capacity of a single node. Horizontal scaling distributes workload across multiple nodes, improving both capacity and resilience. That single distinction answers a surprising number of real-world and interview questions. Scaling decisions are shaped by a deeper constraint, one that appears in every distributed system. You can't fully guarantee availability, consistency, and fault tolerance at the same time. This idea is captured by the CAP theorem. Next, we'll look at it in practice, not as abstract theory, but as something that directly shapes how cloud systems actually behave. End of section 1.1.7.